To motivate the project, the regulation of transportation markets is not a new topic. We've been thinking about regulation of transportation markets for decades. However, what I want to show you is this is a topic that is still very topical still today. These are a few snapshots of media coverage thinking about regulation of transportation markets. Despite historical efforts, the reality that we see in the US is far from being perfect. First, in 2018, it was estimated that the annual cost of congestion was $87 billion for the US. This is coming from the fact that only 10% of the trips in the US take place using some form of public transit. On top of that, the public transit that we have in place is highly underutilized. On average, the average bus is only utilized at 28% of its capacity. Of course, this average masks a lot of heterogeneity because we know that during peak times, buses sometimes run full, but on average, the average bus is running almost empty. And this is despite having very high subsidies already in place. This was a fact that was very surprising to me when I started working on this project. And the fare that you pay, on average, only covers 1/4 of the cost of your total of the trip, meaning that the remaining 3/4 of the cost is covered by some form of subsidy coming from a government. Now, when we want to think about the regulation of transportation markets, we need to think about the objectives that municipal governments have in mind. What are these objectives? The first one is governments want to offer affordable and good transportation. In order to understand how this objective matters, what governments need to know is how prices for different modes of transportation and the quality of different modes of transportation is going to affect the well-being of the travelers. Second, governments want to reduce congestion externalities. In order to understand the importance of this objective, what we need to know is how to map traffic flows, like the vehicles that are running on the roads, into travel times. Third, governments want to reduce environmental and pollution externalities. And in order to know the importance of this objective, we need to be able to map the cost of these externalities in a monetary way, in a financial way, to society at large. And finally, governments do not have infinite resources to solve for this problem. They need to stay on budget. And this is becoming more of a pressing issue. And you might hear the term fiscal cliff, meaning that transportation municipalities are running out of money. And the problem that municipalities face here is that they need to collect money from the fare and tax revenues in order to cover the cost of running transportation systems. Think about paying for fuel or paying for the wages of the drivers of buses and trains. Now, what are the available policy tools that governments have to solve these problems? In this project, the approach that we're going to take is we're going to take infrastructure as given. No, we're not going to be thinking about building new roads, and we're going to keep the residential location and the workplace locations of residents as given. And we're going to focus on policies that target mode choice. Among this set of policies, the first policy that we encounter is public transit subsidies and frequency improvements. And the effect are ambiguous given the objectives that I introduced before. On the one hand, if I make public transportation cheaper, this is going to help travelers. Travelers are going to be happier, especially those who are low income. However, on the negative side, if we make public transportation cheaper, it means that we have to cover larger subsidies, and this is bad from our fiscal point of view. And it's going to have an ambiguous impact on congestion. If you put more buses on the road, this is going to increase congestion, but at the same time, it might induce people who are using their cars to start traveling by bus, so it can go both ways. On the other hand, we have congestion pricing, and probably you know that this is something that is being discussed in New York. And what are the effects of this policy? Mechanically, if you put congestion prices, if you implement congestion prices, this is going to reduce congestion and emissions. It's going to help governments fiscally because we collect revenue, and we can use that money for other means later on. However, this is going to hurt travelers, especially those who cannot easily substitute a way to other modes of transportation. Now, what I want to consider in this research too is that maybe we want to think of a mix of policies. Why is it important to think of a mix of policies? Because maybe we can achieve the best of both interventions, and maybe we can use those revenues that we collect from congestion pricing to invest in public transit. So concretely, what is it that we're going to do in this project? The questions that we want to answer is, what are the welfare gains of different urban transit policies? What are the distributional consequences of different policy tools? How are high-income people being affected, or how are low-income people being differentially affected? More generally, what are the optimal prices and frequencies of different modes of transportation in an urban context? What is the strategy? We're going to model a city planner that is going to maximize a social welfare function subject to a budget constraint. What has this city planner, what does he have or she have in mind? On the demand side, we're going to have travelers that are going to choose across different modes of transportation. These travelers are going to be heterogeneous in their income level. We're going to have low-income travelers, high-income travelers, and they're also going to be heterogeneous in their access to transportation. Some of them are going to own a car, some of them are not going to own a car, some of them are going to be able to use public transit, and so forth and so on. On the supply side, we're going to describe the city as with three equations, or with three functions. The first function is going to be a cost function. Given the number of buses and trains that we have running in the city, how much the government needs to pay in order to cover the cost of this transportation system. The second function is going to be how we map travel flows into travel times. So think about a congestion production function. And finally, we want to think about the monetary cost of environmental and pollution externalities. We're going to take this model to the data, and in order to do so, we're going to construct a novel data set that covers all the relevant modes for the city of Chicago. And armed with our estimated parameters for the different components of the model, we're going to go into counterfactuals and determine optimal policy, meaning optimal prices and frequencies, and measure the welfare effects of these counterfactual policies. This is the roadmap of the talk. I'm going to go into the data, then the model, and finally I'm going to cover the counterfactuals. So I'm going to start with the data, and I'm going to start with the data construction. The first thing that I want you to know is what is the level of observation that we use in this project. So we're going to call our level of observation, we're going to define them as markets, and a market is going to be a thruple defined by origin, destination, and a temporal unit. What is the geographical unit that we use? Is community areas. There are 77 of them in the city of Chicago. This is roughly 40,000 people living in each community area. Temporal unit, we're going to have an hour of the week. We're going to have 48 of them because we have 24 hours in a day times weekend or weekday. This is going to give us roughly 300,000 units of observation. Once we have defined our level of observation, what is the goal? We want to construct a data set that for every origin, destination, hour, and mode, we know the number of trips, prices, and travel times. The sample that we're going to use is Chicago, January 2020. This is for data limitations. We can only focus on winter months. I think it's super interesting to also cover summer months because you do see some seasonality in travel patterns within the year, but this is the best we can do with the data that we have right now. And given this sample, we're going to combine the multiple data sources to construct this objective, this goal data set. What is the first data source that we use? Is mobile phone location data. So probably some of you know that, or hopefully most of you know that your mobile phone devices are collecting data on where you are. Some apps are collecting data on where you are. I'm using that data for this research. So the level of observation that we see there is for a mobile phone device, we can track pings over time. Each of these pings, what I see is the latitude and longitude as well as a timestamp. We're going to keep devices that gives us enough information so that we can quantify whether they are moving or not. And we're going to say that a sequence of pings is a trip if from origin and destination, the first ping and the last ping that we see, you are traveling faster than 11 kilometers per hour on average, and the distance between origin and destination is more than 400 meters away. We're going to call this data set the universe of motorized trips, because with that filter that we are applying, faster than 11 kilometers per hour, we want to get rid of walking trips. Now, this data is not an official data source, so what we did was to check whether we could think of or take off these movement patterns as a reliable source of how about the people in Chicago was moving across space. What I'm showing you there is the distribution of travel distance coming from the pings data, from the mobile phone data, and I'm plotting that distribution against the distribution that comes from a travel survey for 2019 that is representative of the city of Chicago. The fact that these two distributions overlap a lot gives us some reassurance that the movement patterns that we are capturing with the mobile phone data are reliable. Next. The next data source that we use is the individual swipes from your Ventra cards. This is coming from a partnership between the CTA and the co-authors in this project. And basically, we see the tap-in location, the tap-in bus stop or tap-in train station. And we also get an imputed drop-off location. How do we get the imputed drop-off location, even though in Chicago you don't have to tap out? Well, if I see your Ventra car, if I see you tapping at 9 a.m., somewhere and tapping at 5 p.m. somewhere, I'm going to infer that your drop-off location at 9 a.m. is your entry location at 5 p.m. So that's kind of the intuition behind the algorithm that was designed by that paper. The next source of data that we have is the universe of taxi and ride-hailing trips, namely Uber and Lyft. This third data source is publicly available, so if any of you want to start using that data, you can download this from the Chicago data portal. And what we see is the pickup location, drop-off location, timestamp, miles, and fare. We're going to combine those two data sources, and we're going to call this the universe of CTA trips. Now the question is, how do you observe car trips? Because car trips are not recorded anywhere. So we're going to construct car trips as a residual. What is the intuition here? If I see 100 trips from Hyde Park to the Loop at 2 p.m., and I see that 20 of those are by bus, 20 of those are by train, and 10 of those are by Uber, the remaining 50 trips, I'm going to call them car trips. And that's kind of what we do. This is what we do in this research. Finally, demographics. We're going to identify the demographics of a mobile phone device by identifying the model census tract where you spend the night. We're going to assign you the income and the probability of owning a car coming from census, because census gives you the car ownership rates in a given census tract. And we can follow devices over time. Not only we see the income distribution of residents, we also see the income distribution at any origin for any given time of potential travelers. With that exercise, we also did another sanity check to see whether our data was representative at the income level. And what we did here is order tracks according to their income percentile on the y-axis. On the x-axis, what I'm plotting there is the number of mobile phone devices that I identify as being their model census tract, divided by the population reported by census. If our data was completely representative, this should be a completely horizontal line, a flat horizontal line. We're not that far away from that horizontal line. So this was also reassuring that at least the mobile phone data was representative at the income level. Now, the next thing that we did was to put the data in a form that allows us to estimate the components of the model that we need to use to run into our counterfactual. The first component of the model is to understand travelers' preferences for different modes of transportation. So the way we're going to get those preferences is by an approach called revealed preferences, using the observed choices in the data. So with our data set, remember that we observed the number of buses, the number of trips that are done by bus, car, etc., etc. We're going to assume that the number of potential travelers is twice the number of trips that we observe, and we're going to construct choices, the share, the probability of a mode being chosen in a given market as follows. Now, next thing is, remember that there is another piece of information that I need, which is how to map vehicle flows into travel times. So the way we did that is we put the city of Chicago in a computer as a directed graph. The nodes of that directed graph is the centroids of the community areas that I showed you before. The edges are the links between adjacent community areas. And what we did is we fixed a market. Remember that a market is origin, destination, hour of the week. And we fixed a mode, let's say bus, and we query Google to get the route. So we did that for all possible origin, destinations, and hours. And we combined all the routes and all the flows so that for every link at every hour of the day and every mode, we could see how many vehicles were going through each of these links for this directed graph. What do we see in the data? The first thing that we see is that traveling using public transit takes more time. Probably this is not surprising to anybody. Traveling by Uber is roughly the same time as traveling by car. But more importantly, if you wanna choose these faster modes, you will have to pay more money. So faster modes are also more expensive. Why do we see that? So if you look at the graph on the right, for most of the range of the travel speed distribution, the car and ride-hailing dots are above the public transit dots. Public transit, bus and train is flat because you pay a flat fee no matter where you go. And the reason you see an increasing pattern between price and travel speed is kind of mechanical. So trips that take longer, that are longer in distance, those tend to be more expensive mechanically because you spend more gas or your Uber ride is going to be more expensive. But longer trips also are more likely to use the subway, to use highways. And if you use highways, you're more likely, or you are going to be traveling faster. And that's why you see that positive relationship between price and travel speed. Now, this is not part of, we don't need this for this research, but I wanted to show you these patterns because these are, to me, they are very, very interesting. So probably many of you know that Chicago is residentially segregated to a very large extent. That residential segregation translates almost one-to-one to a traveling segregation. So the low-income people, which is the first graph on the left, are going to stay mainly in the south and to the west of the city, and the high-income people are going to travel around the northeast of the city. I mean, this is very interesting. This is food for thought. So, and if you guys are interested in thinking about residential segregation, please come talk to me. Now, how are people of different income levels choosing how to travel? The first thing that we see is that lower income people are more likely to use a bus. Higher income people are more likely to take an Uber. For train, we see an increasing pattern between the use of train and income. Why is that? Because access to trains, or good access to trains, is mostly concentrated in the city center. Think about the Loop. You have very good access to the L there, and that's why you see that you have very that positive relationship. Now, for car, it's an inverted U shape, and this is the product of two things. The first thing is that lower income people are less likely to have a car, and that's why you see that increasing pattern at the beginning. But as soon as you start becoming richer, you're going to start living in places or being in places that have very good access to trains, or you're going to start to use Uber more, and that's why you see that decreasing pattern in the second part of the graph. This trade-off, how people of different income levels are choosing whether to travel by bus, by train, or by car, thinking about the price-time trade-off that I was showing you before, is what's going to inform us later on about how people value different modes of transportation. Now, for when we go back to traffic congestion, something interesting that we saw is that there is a part of the congestion function when we map vehicle flows into travel times that is flat. So let me give you some intuition behind that. What I'm plotting here is two markets. Remember that a market was origin, destination, and hour of the week. So here is origin and destination, and we have 48 points for each of these markets. And what you see at the beginning on the x-axis is the log vehicle flow, so how many vehicles are running through that link. And on the y-axis is the time that it takes to travel through that link. And you see that there is a flat part at the beginning, so no matter how many vehicles are on the road, it's going to take you the same time. So think about when you are driving on a highway. It doesn't really matter if there are 1 or 2 cars, probably you can go at the speed limit. But if there are like 100 cars, probably congestion is going to start kicking in. So that first part tells you that for a range of vehicle flows, you can travel at the maximum speed. We're going to use this later on to inform how we construct the function that tells us how to map vehicle flows into travel speeds. And finally, the last piece that I want to show you is that public transit is very expensive. And this was super surprising to me. What this graph is showing you is if we take the total cost of the buses that are running at any given hour for the city of Chicago, and we divide that total cost by the number of travelers that are at any given time riding in those buses. The flat red line is the fare that you pay. So this graph, what it shows you is the average cost per passenger. The fact that that black line is above the fare that you pay means that gives you the average subsidy that the government has to pay in order to cover the cost of your trip. So what this is telling you is that most of the trips that you take in the city of Chicago across all hours of the day are subsidized to a high extent by the government. Okay. Model. I'm going to show you an overview of the model. I hope I try to be very minimal with equations just to give you a sense of like the intuition, what's behind the economic model that we have in the paper. The details are in the paper. I'm happy to discuss those with you later on. Okay, so this is me. I live in Pilsen, and I have to commute to Hyde Park, J. And I face this vector of prices and travel times, and I'm going to choose like my most preferred mode of transportation. Travel times not only include the time in vehicle, so if I'm driving by my car, the time that it takes to get from Pilsen to Hyde Park, but if I'm traveling by bus, this is also going to include walking times as well as wait times. So we're going to include all of that in the vector of travel times. So I'm going to aggregate over everybody who lives in Pilsen and wants to travel to Hyde Park at 9 a.m. on Wednesday or on Thursday. And that's going to give me the number of travelers. On the supply side, I'm going to have buses, trains, cars, and Ubers running in the city. And there's going to be a vector of prices, and for public transit, we're also going to have frequencies. The total travel time is going to be affected by the number of vehicles running on the roads. So the more cars you have, the longer it's going to take there, but also it's going to be a function of those frequencies. The more buses that are running on any given route, the lower the wait time. The equilibrium in this model, in transportation markets, market clearing comes through travel times. And the same intuition that you have for prices, that prices clear markets, that same intuition is translated to travel times in transportation economics. So think about when you can get to a destination in a very fast way, like by car, there's no congestion. That's going to induce a lot of people to take their car, which is going to increase travel times, which is going to decrease the incentive of people to travel by car. So the equilibrium in this model is going to be determined by that system of equations. Now, this is just for one. I was telling you Pilsen, Hyde Park at 9 a.m. on a Thursday. We're going to do this for the entire city and all locations in the city are connected through the routes that I was showing you before. So we have to solve a problem with 21,000 equilibrium equations. What we're going to estimate is the components of the demand. The components of the demand is how these people are trading off price against travel time, and the components of the time production function. So the congestion production function and how frequency of buses maps into wait times. The government is going to control those things. It's going to control prices of different modes of transportation, as well as the frequency of buses and trains. This is how the government is deciding how to optimally set prices and frequencies. What is this? The first part of this equation is the social welfare function. In the social welfare function, we have consumer surplus, which is the well-being of travelers. The second part of the function is government revenue or profits. And the third part of the social welfare function is going to be environmental externalities. The government takes into account that for every set of prices, there is one transportation equilibrium. So that's the bottom constraint, the second constraint. The constraint at the top is there because I told you that governments do not have infinite resources to solve for this problem. What is that capital B? Well, transportation agencies get some money, typically from property taxes, to run transportation systems. In the case of the CTA, this is $11 million per week. So that means that the CTA is short $11 million per week because they don't get enough money from the fares. So they are getting $11 million from property taxes in order to run the transportation system that we have. Demand, as I said, remember the market definition that I told you, origin, destination, hour of the day. We're going to have an exogenous number of travelers at every given market. Every traveler, I, is going to choose their most preferred mode of transportation in a sequential way. First, these travelers are going to choose whether to travel or not. And if they want to travel, they're going to choose their most preferred mode of transportation. And that choice set is individual specific. Why is it individual specific? Because if you don't own a car, I'm not going to let you to travel by car. Or if you don't have access to trains, I'm not going to let you take the train. The utility, you're going to choose the mode of transportation that gives you the highest utility. What are the components of this utility? First of all, you're going to have some disutility from having to travel for longer or to wait for longer. You're also going to have some disutility from having to pay, like you don't want to pay. That's like the law of demand. And that disutility, we're also going to allow it to differ by income. So we're going to allow the disutility of prices from lower income people to be different from higher income people. We're going to have other components into the utility, but the findings that we get when we take this model to the data is that the value of time, which is like the key statistic for transportation economics, meaning how much you value 1 hour of your time while you are traveling, is roughly $13.5 per hour. Just to give you a sense, the transportation literature finds that the value of time has to be roughly half the hourly wage of the location. The hourly wage of the location for the city of Chicago in 2019 was $30. So we are pretty much in the ballpark of what the literature has found. And interestingly, we find a lot of dispersion in the value of time between high-income people and low-income people. We find that lower-income people are way more sensitive to prices than higher-income people, and that tells us that, or it's translated into lower-income people having a lower value of time than higher-income people. Transportation technology. So I told you how we're going to get the preferences, how these people are trading off different modes of transportation given prices and travel times. Now I'm going to tell you the supply part of the model. So I'm going to tell you how we want to map from traffic flows into travel times. And that's going to be different by different modes of transportation. By private cars, it's only the time that you spend in your vehicle. Public transit is time in vehicle, walking, and wait time. And private transit, which is Uber and Lyft, is wait time plus time in vehicle. We're going to everything is going to be a product of our model, but walking time that I highlighted in gray, that walking time, we're going to keep it as exogenous and we're going to take it from Google Maps. Remember the city that we model it as a directed graph? So we're going to use that data. Remember that I was constructing the number of vehicles across different modes that are going through a link. I'm also going to be able to observe the time that it takes to go from a given link that you can query from Google Maps. And what I'm going to do is I'm going to map the number of vehicles that are going through a given link onto travel times. And then for an entire route, I'm just going to sum the travel times across different links. And remember this graph that I showed you before that has this flat part and then the increasing part? Well, we also see that there are differences across different modes of transportation conditional on the same link. So we're going to allow for heterogeneity by mode of transportation, and the supply or the congestion function that we estimate is that at the beginning, you are at the flat part, but as soon as congestion starts kicking in, we're going to estimate a log linear function, and that's what that function is telling us. The findings is that the car congestion elasticity is minus 0.17. The benchmark in the literature is minus 0.15. One thing that we observe is that traveling by bus is the travel time by bus is way less responsive to traffic than traveling by car. So cars are more sensitive to traffic than buses, which is something that probably one should expect. Now, let me move on to counterfactuals. So what I've done so far is I've estimated the demand part of my model, the supply part of my model. With demand and supply, for any set of prices, I can construct the equilibrium because I just solve for the equilibrium in my computer. And what I'm going to show you now is how we should set these prices optimally. The benchmark is going to be the status quo, which is what we observe today. And the counterfactuals that I'm going to show you today is this budget-constrained government that is maximizing welfare. The policies that this government is considering for today is uniform pricing across space and across time. The constraint set, we're going to run 3 counterfactuals in which I'm allowing the planner to play with different instruments. The first one is the transit counterfactual, in which the planner is kind of the CTA, is thinking about the prices of buses and trains as well as frequencies. The second one is thinking about congestion prices, and the third one is considering the mix of both. Okay, so let's go into counterfactuals. The first column on this table is the status quo. So this is what's happening today. The first that you see is 1.09 and 1.33. The fare for buses is 225 and 250. Why am I showing you fares that are less than that? This is because a lot of people are paying discounted fares. So when you take into account the discounted fares, this is the average fare that one traveler pays. And yeah, so I just want to say that about that. So the first counterfactual that I'm running is, remember, I'm going to let the Transportation Authority to optimize our prices and frequencies. And I'm going to do that at the beginning, allowing the government to not be fiscally constrained, allowing the government to have infinite resources to solve for this problem. What is it that we get? Well, we get a super interesting result that the planner wants to pay people to ride public transit. Why is that? Because if you pay people to ride in public transit, this is going to move a lot of people who are using their cars into public transit. That is going to help in both ways, through congestion externalities, but also through environmental externalities. Now, when the planner looks at, in that problem, the planner also sees that because buses are underutilized, it's optimal to reduce the frequency of buses by 20%. But because trains are not so underutilized as buses, the planner finds that it wants to increase the frequency of trains by 20%. How much money the planner needs to implement this equilibrium or this allocation? Remember that the CTA needs $11 million already in the status quo. So if the planner wanted to implement this allocation, the planner needs extra $9 $8.56 million on top of those $11 billion. Is that feasible? Probably not. So what we do next is actually allow the planner or force the planner to stay on budget. When we do that, things don't look so great in terms of like public transit prices. We cannot get to negative prices, but we get to prices that are 50% low. Now, because you are budget constrained and you have to stay on budget, this implies that you have to reduce the frequency of buses even further, and you cannot increase the frequency of trains so much because you are collecting less money. You are subsidizing public transit even more. You have fewer resources from revenue collection. Therefore, you have to cut down costs somehow. When you do that, you get welfare gains of $11.5 million per week. You divide that by the population of Chicago, 2.7, and you get the gain per person. Half of that is going to come from travelers being happier, and the other half of that is going to come from a reduction in environmental and pollution externalities. What we do next? The next policy, one thing that we have in the paper, and I don't think I have time to cover it today, is that we have a theoretical way of decomposing each of these optimal prices that we get, where the sources, each of the channels that go into the optimal prices. I'm going to leave the details for the paper, but it's nice to understand because each of these channels, because you can think of like policies that are targeting different margins, and maybe that's a good way of informing policymakers of how we should regulate public transit. If anything, what we get from the bottom line that we get from these counterfactuals is that if you want to make public transit cheaper, you should give the government more resources. That's one of the takeaways from this counterfactual. Now we're moving to road pricing, so congestion pricing. What do we find? We find that the optimal congestion tax per kilometer is 37 cents. Just to give you a sense of what this means for the average traveler, this is $14 per day for the average commuter. I don't know if you are aware of other congestion policies that are already in place in the world. For London, the cordon pricing that is being implemented is £23 if you enter the city center. The one that is going hopefully to be implemented in Manhattan is $23 if you enter Manhattan below 60th Street. So at least our numbers are in the ballpark of things that are actually being implemented. When we do that, we see that welfare increases by 4.2 million per week. So this is almost threefold what we saw before. So another takeaway is that congestion pricing on efficiency grounds is way better than intervening on public transit alone. However, this is very bad for consumers. Consumer surplus decreases by 25%. Why is that? In the city of Chicago, 70% of the trips are done using private cars. So you're hurting 70% of travelers. So another takeaway is that even though congestion pricing is very good on efficiency grounds, it's very bad in terms of redistribution. However, one nice thing about congestion pricing is that it's way more effective to reduce environmental externalities, and you collect so much revenue. Now the city surplus is positive. It went to almost $25 million per week. You collect so much revenue that you can fix this regressive effect of congestion pricing by giving all of this money back to consumers. Finally, what we do is the combination of these two policies. And what we see is that actually you can implement the best of both worlds if you do the combination of these two. Public transit becomes virtually free. You will have to pay 7 cents per bus ride or 10 cents per train ride. Congestion pricing remains on the same order. You get the highest welfare gains if you combine both instruments. This is kind of a mechanical effect of the model because you are giving the planner more flexibility. And in this scenario, this revenue that you are getting from congestion pricing actually fully compensates the loss in consumer surplus from having to pay higher car prices. And this is the composition of that congestion price that I was mentioning before. More of the details in the paper. And I'm just going to conclude because I think I'm almost out of time. What we did for this paper is to construct this novel data set across all modes for the city of Chicago, a major urban area in the US. By the way, we're hoping to make this data set publicly available. So if some of you is interested in working in transportation issues or in urban issues that might find this data set available, please reach out to me. With this data set, we estimated the model that I showed you before. We compute optimal price subsidies at public transit frequencies. And the two results that I want you to take away from this talk is public transit should be almost free. However, governments cannot fully implement that right now because of budget considerations. Transportation agencies are fiscally constrained. Second, we can use road pricing, congestion pricing, to actually collect revenue and implement the optimal public transit policies. But if you don't rebate the money back that you get from congestion pricing back to consumers, congestion pricing is highly regressive. So that's it. Thank you so much for listening.